So the question we didn't answer here, it's the same game. Same game we were playing up here, right? Where if you roll a 6, you win $100. You don't roll a 6, and then on the second roll, you roll a 6, you win $50. And if you don't roll a 6 the first time, you don't roll a 6 the second time, you don't win anything. Okay, that's the game. That's the game we were playing with. We were playing yesterday, or that we came up with the table for the probability model. Okay, so we talked about that. So if I play once, I would expect to win $23.65 in the long run, right? With a standard deviation of $38.19. Okay, so that same game. For part C is, what if I were to play it 200 times back to back? Sit down and play it 200 times back to back to back to back to back to back. How much would I expect to win? Not after once, after all 200. Okay, because after once it's $23.65. If I played it once, that's the average. That's what I would expect to come up with. Now, what if I played it 200 times? So the table is based off of one time, right? If I play it one time. So that means 200 tables exactly like this here. 200 tables like that, right? So that means 200 times, what am I going to get as a mean? There you go. If we're going to get, if all of the tables, the game's the same. And for each game is an average of $23.65. And I play it 200 times. For each of those games, you have an average of $23.65. So this is, I'm multiplying 200 times what it was before, which is $23.65, right? We'll get there in a second. That one's a little more complex. Yeah. So 200, let's see, $470, 400, it's 400 something, isn't it? 447, 730 cents. Say it one more time. $4,730 and how many cents? No cents. Clean. So if I play the game, sat down and played the game 200 times, back to back to back to back to back to back, all 200 times. After 200 times, I would expect to win $4,730. Okay. Standard deviation is a little more complex because standard deviation, I'm playing the game back to back to back to back to back, right? So it's kind of like what I did with B, but 200 times. So this is kind of like what I'm doing here. Watch. So I'm finding the standard deviation of 1 time plus 2 times dot 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 200 times. Well, that's exactly what I'm going to do with my calculations, right? So we have a square root. What's the standard deviation for one game? 38.186 squared plus what's the standard deviation of the second game I play? It'll always be the same, right? Plus dot dot dot. The last game, the 200th game, the standard deviation will still be the same, right? Now, is there a faster way I can use my calculator to do this?
Can you add the exponents together?
There you go. Aren't we just squaring the same number and adding it 200 times? So figure out what that number is that you're squaring it, multiply it by 200, since there's are 200 of them that you're adding up together, take the square root. So the number you're squaring is, yeah, go for it. Step outside. The number you're squaring is 1,458.171. You're going to get that number 200 times, and you're going to add them all up. So instead of adding them all up, multiplication is a fast way of doing that. So when you add all of them up, you're going to get 291,634,119. Take the root. Okay. So it doesn't matter if I play 2 times or if I play 200 times or 2,000 times. The steps are going to be the same, right? For expected value and for standard deviation. So I should write it like this. 1, 2, ... 200. Times the mean. Sorry, I'm just rewriting what I did earlier. Okay. All right. Okay, so the last problem, the very last problem. So this one, the one we've been doing, this was discrete, right? There's only 3 things that could happen. They're countable: 0, 5, 50, and 100. The last one is an example of of continuous. And I'll explain why in a second. This question was actually a test question. It was a test question, but now I put it in the notes instead. Okay, because it is that type of AP question where I've seen similar to this a lot of times. So I decided to take it off the test and put it on the notes because of that reason. Okay, so here we go. We got a bike store. Okay, the bicycles arrive at a bike shop in boxes. So the bike shop doesn't make the bikes; they order the bikes from someplace. The bike shop puts them together and then they sell them to the customers. Okay, that's how most businesses work. Very rarely do businesses actually make like from scratch, right? So that's what the bike store does. Okay. So the average times and the standard deviations for setups are given. So the average time it takes the workers to unpack a bike when they get it in is about 4.5 minutes. I believe this is minutes. Doesn't say, but I believe it's minutes. Yeah, it makes sense, right? With a standard deviation of 0.7. Assembly. So once they unpack it, put the bike together, takes an average of 21.8 minutes with a standard deviation of 2.4. And then the last process is tuning the bike up to get it ready for the customer. It takes 12.3 minutes with an average of 12.3 minutes with a standard deviation of 4.7. Okay, so this is important as well because all of these times it says are independent and they are normally distributed. So anytime you see the words normally distributed, and they're asking you to find probabilities, more than likely we're going to do what we did for this problem right here. More than likely you're going to do something like that, okay? So let's see the question is. A customer decides to buy a bike like one of the display models, but wants a different color. The shop has one still in the box. Okay, so it hasn't been unpacked, it hasn't been assembled, it hasn't been tuned. The manager says they can have it ready in half an hour. Find the probability that they can actually do it in half an hour. Okay. So on average, how long does it take them to go from unpacking the bike to ready to give it to a customer? How do I figure that out? Add all the means together, right? Add mean 1 plus mean 2 plus mean 3. So on average, how long does it take for them to have a bike ready to go for a customer?
38.6 minutes.
Okay, so let's write that down. Okay, so the mean of unboxing plus assembly plus tuning is, what was it, 30.6 minutes. What about standard deviation? How do I figure that out? No. Haven't been paying attention. What do we do with standard deviations? There you go. All right. Just like we did here, right? We're combining means. Anytime we combine means, we're going to find the square root, or standard deviation squared plus standard deviation squared, however many there are, and then square root them. Okay. So there are 3 standard deviations. So I got to square each of them, add them together, and that'll be the standard deviation for all of them. 2235.
5.3235.
326. So they want us to find the probability that we can get a bike as assembled. Well, on average, how long does it take them to build a bike? And what did they promise?
30.
So already, it's probably not going to happen, right? Or the chances of it happening are pretty low. So we have to figure out exactly what are the chances that it would happen. Well, it said normal distribution. And what did I say? Most of the time they want probability and they want normal distribution. Start with the curve and the mean. What's the mean? 38.6. There you go. That's the average time it takes to assemble a bike. What is the value that we're trying to measure? 30, right? Okay, so 30 is less. So 30 would be somewhere over here, right? And are we going to shade above or below? Why below?
Because we're trying to find 30 or less.
There you go. We're trying to figure out the chances that they can keep their promise, which is here. In the shaded part, they kept their promise. Outside the shaded part, their promise wasn't kept. Do the rest. You guys can do the rest. Figure out what percent is going to be in there. What percent chance? What is the probability, or what percent chance that they keep their word? Okay, so the probability, 30 is the number that we're trying to figure out what the percent is. So again, we said it was going to be a low chance because the average is 38.6, almost 40 minutes on average, and they promised it within 30. So we knew it was going to be a low chance. So the chance is pretty low. It's a little more than 5% chance. Okay, not a good chance that it's going to happen. Okay, it's not zero. It is possible. Okay, all right. Last question. What is the probability that the tuning stage takes longer than the assembly stage? Okay, so let's go to the tuning stage versus, so this is tuning stage versus assembly stage.
Tuning is longer?
Tuning is longer, or sorry, no, assembly stage is longer. Assembly stage is, on average, assembly stage is longer by what, 9.5? Okay, so on a normal day, assembling a bike is going to take about 9.5 more minutes than tuning it, right? So what the question is asking is, what is the percent chance that the opposite is true? That tuning the bike takes longer than assembly. So in other words, they're asking, what's the probability that different color, that this guy is going to take longer than this guy, when this guy right here has a history of taking 9.5 minutes longer, right? So we're comparing tuning versus assembly, right? So what are we looking for? We're looking for when tuning minus assembly is what? Say what? So if tuning takes longer, T should be bigger, right? So what? No, exactly what you were saying. Is positive. That's what we're looking for. When I subtract those two, and it's a positive number. Okay. Now, on average, tuning minus assembly is what? It's usually negative, right? And it's negative what? Negative 9.5 minutes. That's the average, right? Picture starting to become a little clearer. What goes in the middle?
Negative 9.5.
The average always goes in the middle, negative 9.5. What am I looking for? What type of numbers am I looking for that will give me what, and be able to answer the question? Positive numbers. Numbers that are positive. So which way are the numbers positive? To the left or to the right? To the right. So what number does it have to eclipse to get to positive? 0. So I'm looking for these guys right here. We're going to need that too, right? Yeah, we're definitely going to need standard deviation. This is a setup here, right? So we got a z-score. Z-score is 0 minus a negative 9.5. So it's actually going to be a positive z-score. But yeah, we need standard deviation, right? We never did standard deviation.
5.277.
Wait 1 second. How did you come up with that?
Square root of 4.7 to the second power plus 2.4 to the second power.
So we need to find that, right? The difference is t minus a. So say it again.
4.7 to the second power plus 2.4 to the second power. And then
4.7 to the second power. 4.7 comes from where?
the square, the standard deviation of tuning.
Tuning?
Tuning? One of them. Tuning, yeah.
Okay. Plus, and tell me the other one.
2.4 to the second
Squared, which comes from the standard deviation of
power.
assembly. and then you add them together, square it, add them, square root it, and what'd you get?
5.272.
Yeah, the biggest mistake I see is when students just add when they're combining standard deviations, they just add them. Oh, 4.7 plus 2.4. No, you gotta multiple. It's a different animal that you're tackling. Okay, so we're gonna get positive 9.5 because 0 minus a negative is positive 9.5 divided by the standard deviation. So you pretty much get 1.80. Okay. Positive 1.80 leads me to 9641. Yep. So is 9641 going to be the left or the shaded part that I want? 9641. Good. So how do I get the shaded part I want? Subtract it from the whole. 0359. So the probability of tuning taking longer than, what's the other one? Assembly can happen, but very small chance. But it can happen. Okay. So some questions you're going to see this chapter, you're going to see normal distribution, stuff with normal distribution. If they have stuff with normal distribution, you're more than likely going to be doing this setup. Okay. So to do that, you're going to need a mean. You're going to need a standard deviation. Once you get that, and then go back to what question are they asking me and what am I trying to figure out? Okay. All right. Yep. Then you get to break out your z-score table and you go from there.